Hello everyone, today let's take a look at QP113 where we have 100 noodles in a soup bowl. So you are blindfolded and told to take two ends of some noodles where each noodle has the same probability of being chosen and connect them. And you continue until there are no free ends. So what is the expected number of circles at the end of this process? So we have 100 noodles in a bowl here. Let's just think about what's going on first, right? These are my noodles right here. They basically have two ends, right? As noodles do. Okay, so ... we have 100 noodles here. So if I just grab a random end of one of these noodles, let's see where I can connect it to. Now I can connect this end of the noodle to any of the remaining ends of noodles, right? So if I happen to choose the other side of the exact same noodle and connect them, well then I'm basically just going to get a circle. It's going to look like this. Now instead, let's go back to that same situation. If I have this end of the noodle and I'm trying to connect it somewhere, if instead I choose the end of a noodle on a different noodle and then connect these, well, I'm not going to have a circle anymore. This end of the noodle is going to be connected to this one. It's going to just look like this, a really long noodle. So now going back to the original situation, I have two options. Either I connect my end of the noodle to the other end of the exact same noodle, or I connect it to one of the ends on one of my other noodles. When I connect it to the other end of the same noodle, I get a circle, and when I don't, I do not get a circle, right? I just get a longer noodle. So now maybe you can see the recursive nature of this question. If I choose an end of a noodle that is not on the same noodle, so I form a mega noodle like this, well then I'm just going to find myself in this situation where I have 99 noodles. And if I connect it to the one on my same noodle, so I make a circle, well now I have a circle, and again, I still have 99 noodles remaining. So with these recursive problems, we're always going to be starting from the base case. So let's just start off when we have one noodle. Let's calculate the expected number of circles. So if I let x be the random variable denoting the number of circles, well then the expected value of x when we have one noodles, which I'll call e sub 1 of x, is just obviously going to be 1 because we only have two ends, and when we connect them, we're going to get a circle. Okay, super simple. Now let's look at the case when I have two different noodles, and let's calculate e sub 2 of x, the expected number of circles when I have two noodles. Well, I'm going to start by choosing one end of a noodle. Let's say it's this one right here. Now I need to choose my second. So once I've chosen my first end, I have three ends remaining, and we know that they all have the same probability of being chosen. So these are all going to have a 1/3 probability of me choosing them when I'm blindfolded. So I have a 1/3 chance of pairing up this end with the other side of the exact same noodle, in which case I'll get a circle. So my expected value in that case, which happens with probability 1/3, is just going to be equal to 1. And now I find myself in the situation where I have one noodle. So 1 plus the expected value sub 1 of x. Now if instead I happen to choose one of the ends of the other noodle, well then I'd form a mega noodle, and that would happen with probability 1/3 plus 1/3, right? So 2/3 chance that I form a mega noodle, and in that situation I just end up in the exact same situation that I was back here. So 2/3 chance that I have 0 circles, but I still find myself back in the same situation, right? So e sub 1 of x. So to actually work this out, I can just plug this in right here, and I'm going to get 1/3 times 2 plus 2/3 times 1, which is just going to be equal to 2/3 plus 2/3, so 4/3. Okay, so now let's move on to the situation when we have three noodles. I'll draw that out right here. So 1, 2, and 3. Now what is e sub 3 of x, our expected number of circles for three noodles? Now let's just say randomly my first end selected was this one. So now what's the probability of selecting each of my other ends? Well, they're identically distributed, and we have, how many do we have? We have 5 of them, so they all have a 1/5 chance of being selected. And again, if I select this end with probability 1/5, I'm going to get one circle, and then I'm going to find myself back in the exact same situation. This is going to be a circle, and then I'm going to have two noodles, so I'm going to have e sub 2 of x, right? So I add on e sub 2 of x here. Okay, now instead, if I select one of any of the other remaining noodles, so 4/5 chance that I select any of the others, and when I do, I'm going to have a mega noodle right here and no extra circle. So I'm just going to find myself back in this exact situation, right? So 4/5 chance of e sub 2 of x. And we just calculated the expected number of circles when we have two noodles, so we can just plug that in right here. I'm going to plug in 4/3, and when I do that, I'm going to get 1/5 times 1 plus 4/3, which is just going to be 7/3, and then I'm going to add that to 4/5 times 4/3 right here. When I work this out, I get 16 plus 7, so 23 divided by 15. Okay, now let's try to generalize this to n different noodles, right? So if I have n noodles right here, I'll draw them all out. Boom, boom, all the way down to my nth noodle. Okay, again, I choose one of my ends. What are my odds of getting the other end of the same noodle? Well, how many ends of noodles do I have? Well, each noodle has two different ends, and we have n noodles, so we have 2n ends of noodles. However, I've already chosen one of my ends to pair up, so that leaves us with two 2n minus 1 remaining options that I could pair it up with. All of the ends except for this one right here are going to give me a mega noodle, and when I choose the other end of the same noodle, I'm going to get a circle. So those are my two options. So my odds of choosing the same end of the noodle are going to be 1 out of 2n minus 1. Now my odds for a mega noodle are going to be, well, I have 2n minus 2 remaining ends that are not a part of this one, right? So I have 2n minus 2 out of 2n minus 1 chance of making a mega noodle. So now we can calculate my e sub n of x just like we were doing before. We know that with 1 out of 2n minus 1 probability, we're going to have one circle, and we're going to find ourselves in the situation where we have n minus 1 noodles, and we can take the expected number of circles that we find in this situation, right? Now I have a 2n minus 2 out of 2n minus 1 chance of making a mega noodle, and in that situation, well, I'm going to have 0 extra circles, and I'm just going to find myself back in the situation when I have n minus 1 noodles, and then my expected value in that case was just e sub n minus 1 of x, right? Now when I simplify this, I get the recursive property of this basically equation. I get e sub n of x is just going to be equal to basically 1 on 2n minus 1 plus e sub n minus 1 of x. That's just because this term right here plus this one times this one, when you expand this out, is just going to be equal to this one, and then we have this one over here, right? So essentially now I know the recurrence behind this problem for a general n, so I can basically just simplify this. I'm going to move this over to the side so we can do that. We know that e sub n minus 1 of x follows the exact same recurrence relation, so we know that e sub n minus 1 of x is just going to be equal to, well, if we plug in n minus 1 for n here, we're just going to get 1 on 2 times n minus 1 plus e sub n minus 1, which is n minus 2 of x. And then on the bottom right here, this is going to simplify obviously down to 2n minus 3. So basically we can replace this term with this. Also, just to keep it clear, this is the recurrence relation that we found here. So now we can use that to break this term down too, right? Similarly, in the exact same way, we know that this is just going to be equal to 1 over 2 times n minus 2 minus 1 plus basically e sub n minus 3 of x. Okay, so now I'll replace this term with this. Once I've done that, now you can see the pattern, right? These are going to be our odd numbers right here that we're subtracting from 2n as we keep on going. So next we're going to have plus 1 on 2n minus 7, and then we're going to have 1 on 2n minus 9, and then we're going to keep on going all the way down till we get to our base case, which was e sub 1 of x. Now if we plug 1 in for k into our nifty little recurrence equation over here, we're just going to get 1 on 2 times 1 minus 1, also known as 1 on the bottom. So this whole term right here is going to be 1, and then plus e sub 0 of x. This is obviously just going to be equal to 0. So we found our final term of 1. So now how many of these terms are we summing up? Well, this one right here was in the e sub n recurrence. This one here came from the e sub n minus 1 recurrence. And then this one here came from the e sub n minus 2. This one here came from the e sub 1 of x. We're summing from 1 all the way up to n of these terms. Now actually, to get this in summation notation, it's going to be easier just to write it in terms of how it was before, right? So this one came from the fact that we were plugging in n minus 1 into our equation. So this was this, and then this right here came from the fact that we were plugging n minus 2 into our equation. This one came from the fact that we were plugging in n minus 3 into our equation, and this one came from the fact that we were plugging n minus 4 into our recurrence equation, this one up here. And this one right here came from the fact that we were plugging 1 into our recurrence equation, and it was 2 times 1 minus 1. So this is going to make it easier to understand in summation notation. Basically, what are we doing? Well, we're just iterating through this value right here, and it's going from n to n minus 1 to n minus 2 to n minus 3 to n minus 4, all the way down to 1. So therefore, all we're doing here is taking the sum from basically, let's say our iterators k equals 1 to n of 1 over 2 times k minus 1. Okay, so this right here solves it for general n, but we didn't even need it for general n. We just needed it for n equal to, what was it, 100, right? So now let's just plug in 100 to this formula right here. And when I plug in n equals 100, the only n in this thing is going to be the top of our iterator. This is what I get. There's no really closed form way to simplify this other than writing it in terms of harmonic numbers, which would just give us some h's. But basically this right here is our final answer. So it's basically just going to be 1 over all the odd numbers. You notice that these are odd numbers between basically 1 and 2k. So if you were to do it out, it would just look at 1 plus 1/3 plus 1 on 5 plus 1 on 7 plus ... all the way up to plus 1 on 199. So again, no easy way to solve this just by doing it with a computer. When you do so, you get something along the lines of 3.28. So the expected number of circles as our noodles grows very large is not even going to be that high. It's going to grow basically logarithmically. We know that the harmonic numbers grow logarithmically, so even if we have 1,000,000, it's still only going to roughly be like 7 circles that we're going to get, right? And that makes sense because as the number grows larger, we're less and less likely to form a circle, and we're just going to keep forming bigger and bigger mega noodles, right? So to conclude, this right here is our final answer.